Welcome everyone to another DeepThought Summer Student Talk, today presented by Benjamin Hertzsch, who's talking about his Summer Student Project within the DeepThought Alpha project on autoencoding star formation from cosmological parameters. So yeah, please.
Thank you all for joining, also from my side. In the last talks, the previous speakers talked mainly about physics and also going towards biology. Today, I want to change a bit what we're going to talk about, and I want to present instead a computational method that can be used hopefully later within this DeepThought Alpha project. So let's go. I'm briefly going to give a short introduction what we are speaking about, actually, with the multiverse and everything. Then I want to talk about autoencoder, since, you know, from the title, my project is about autoencoding cosmological parameters, or star formations from cosmological parameters. So I want to briefly present what autoencoders are and the variants. And then I want to speak about precisely how we can use that for actually modeling cosmic star formation, for retrieving information. And the second half of my code, so it's going to be roughly the last 15 minutes, I want to actually show what I've written over the summer, which is a script with which such an architecture can be built. And well, the respective data analysis operations can be performed on data. So let's get going. The multiverse arises as an idea in several possibilities, say, for example, in internal inflation or string theory. However, we can also just very naively ask the question of what is the statistical playground of cosmological parameters to allow for the emergence of intelligent life within our own universe, for example. And this has been extensively studied in Adams, in a review by Adams in 2019 for single variations of cosmological parameters. So for quite a plethora of parameters that is available, including standard model parameters, but also purely cosmological parameters, respective ranges have been found that allow for a viable universe. Now, the obvious question arises, what happens if we vary multiple parameters at the same time? Because this is, of course, not as trivial, because the same ranges might not immediately apply. Yes. So given that we are somehow looking for a multiple variation, what we are after in the end is the question of how likely is it that life emerges, that an intelligent observer emerges. And for this, we can use cosmic star formation as a proxy. There's a chapter written on it in this paper on which the first talk on this channel was given. So if you go back to this talk, you can all see that. In this paper, there is a comment on how, say you have simulated the cosmic star formation history and you know the metallicity of your cosmos at all redshifts too, then you can crudely calculate or estimate the terrestrial planet formation rate and hence also the emergence of intelligent life. Well, say using a normal evolution time of an intelligent species, or what we think a normal evolution time would be. So what we want to eventually do is we want to simulate multiversal star formation rates and retrieve information from that. Here the question is if we find some efficient way to compress the plethora of available cosmological parameters to a few relevant ones. If you think it in a pictorial way, this could, for example, be that we take a handwritten picture of a 2, here, say 100 times 100 pixels, and we represent it in a very low dimensional, say here 10-dimensional representation of pixels. And we hence want to reconstruct something. So this picture could correspond to 100 times 100 cosmological or multiversal parameters, for example. But I want to already make you aware, because this is where we will vary this variational autoencode idea later. Our comparison scale will not be the cosmological parameters themselves, but the equivalence of universes, which is measured by the congruence of the star formation rates. So if we can describe two universes with seemingly different conditions by the same cosmological, by the same star formation rates, then they might be equivalent for us as for the question of life. Good. So what we will use for that is an autoencoder, or what is called an autoencoder network. So what is a simple autoencoder? The concept was actually already introduced by Hinton, this guy, in the 1980s, but then formally rediscovered in 2006 with a paper where they presented a network to compress data to a low-dimensional representation. So this network takes an input vector x of data, say, for example, some picture like this. It then encodes it down to a low-dimensional latent variable dimension of the dimension that will be henceforth called latent dimension. And then it compresses this out to the right side to a vector x primed. And the discrepancy, the loss of this model would then be if the two vectors are identical, if x and x prime coincide, which could, for example, be measured here by this chi-squared loss function. Good. The advantage of this network is that these two networks, essentially this encoder and this decoder, they can be considered separate networks, which, simple sequential models, not too difficult. However, when stacked together, the error can be propagated through the whole network, and so the weights can be trained for the one big network at a time, and we still have this interesting latent dimension, so that's an advantage. Yes, autoencoders, this simple form already of autoencoders has many practical applications, including dimensionality reduction, denoising tasks for pictures, for example, to remove noise in, say, handwritten pictures, anomaly detection. And in general, you might think that the operation is quite similar to principal component analysis when you compress this down to a latent dimension. And this is somehow true. However, these autoencoders generally outperform the principal component analysis due to their nonlinear nature. A comment on that is in the paper by Hinton. There are, however, unresolved issues with this autoencoder because the method at hand is not fully developed for, say, for our task, for example. We would be interested in having a latent dimension that has as much information as possible. And this would, for example, be that we want our latent variables to be orthogonal to each other. And also, it might be actually interesting to see if with these latent variables, we can generate new data. That is, we can generate new star formation rates that look similar to another one and see how the parameters change under this. Well, such a generative method was presented by Kingma and Welling in 2014 with a model that extends the simple autoencoder. And here the crucial difference is that while the simple autoencoder compressed one point in input space, that could be, say, for example, if we are considering an input of 10 cosmological parameters. So then we have this point that is represented by a tuple of 10 numbers. And this is compressed to, say, a tuple of, 3 numbers if we have a latent dimension of 3. Now, in this variational autoencoder, we will compress this to a distribution over 3 dimensions. And from this distribution over 3 dimensions, we will then be able to sample this latent variable, which would be a tuple of 3 numbers. I will show this on the next slide, so don't worry. What I also want to write already here is there is an additional loss term for this distribution. That will be very convenient, as we will see in just a moment. And as a rather incredible feature, despite the stochastic nature of sampling, backpropagation will still be working in this network, as we will see. So this would be a variational autoencoder model. It looks rather similar to what we had before, but the big difference that you can see here is that the input is not directly compressed to a low-dimensional representation Z, but instead it is compressed to 2 vectors of the same length, mu and sigma, which represent together a distribution or several distributions. And what we practically do is we want these distributions to be diagonal Gaussians, by which I mean that every entry in this vector or in this tuple would be represented by the ith entry in, or well, if we the ith entry in this vector Z would be represented by a Gaussian distribution with the parameters described by the ith entry in this mu and sigma vector. So yes, more on that on the next slide. We see that still our loss function will be determined by the input and the reconstructed input, and if they are identical. And on the right side, we still have a decoder. Now, I don't want to speak too much about these conditional probabilities here and these parameters. This is very interesting and very nice information theory, but I'm afraid there is no time for this in this talk. Instead, you can actually read the paper by Kingma, which presents that in nice detail. Good. So on this slide, I briefly want to summarize the key differences or what this variational autoencoder is doing to work. First of all, as I mentioned now already, now for the third time, the encoder maps a point in input space X, not to a point Z, but to distributions defined by mu and sigma. The decoder then takes a latent variable and maps it to some reconstructed output space point. And the latent variable Z is sampled from these distributions. Now, sampling itself is a stochastic process. So we expect this to not work for a neural network because backpropagation would be spoiled here at this stage. However, we use the reparameterization trick that will allow this network to still be working. You can see this on the right side here in this plot. In the original form, we would have Z as a random node, which, this would be the case if we sample from a distribution described by phi and x. However, in the reparameterized form, we will have that we introduce an auxiliary node epsilon here on this side, and we then write Z as a deterministic function in the parameters phi, x, and epsilon. Practically, what we would do for our diagonal or Gaussian idea is that we take Z to be the mean of the respective distribution plus the standard deviation times some random epsilon, where epsilon itself is the sampled variable, which is sampled from a normal distribution. Yeah, and this operation is meant to be element-wise for each of the entries of Z. So if Z is a three-dimensional tuple, then say you would have an index I here that runs from 1 to 3. So in this diagonal element-wise form. Okay, and then we also have a new loss term, as I mentioned already. This will be the KL divergence, as it's called. I'm writing this explicitly here because if you happen to read through my script later and in the functions, it might be useful to understand what's going on. This loss term, very crudely speaking, is somehow measuring if our Z distribution that the network is learning can actually be described by a diagonal Gaussian. And this would be a loss term. If you do the mathematics, you will find that when you optimize the information from the neural network, this additional loss term will show up where the I runs over the latent dimension. So this would be, for the example of a latent dimension of 3, this I would take values 1, 2, 3, and these then the respective entries of the learned distribution vectors. The takeaway message from this third point is that this KL divergence term acts as a regularizer for our learning process, and it will actually be a very nice feature because it allows for a disentangled representation that we are learning. This has been extended in this paper by Higgins and others in 2016, where they considered early visual concept learning. They generalized the variational autoencoder concept, and they applied it to how geometric information about objects would be stored. Well, the idea is that they wanted to learn what's going on in the brain. And while this plot on the right side is a bit difficult to understand at first, and also I'm already running over time, as I can see, for final measure time. Anyways, we can see here in these latent variables that while they were trying to compress data to a 10-dimensional representation over 10 latent variables, they are very disentangled in that every latent variable represents a new feature. 5 of them are completely switched off, or more or less completely switched off. And the first 5 latent variables, they will represent the y position of a geometric object, the x position. So you can see that here, how the y position is varied, the x position as we vary this latent variable, and then also the scale and the rotation of the object. So this is very nice because this gives a very powerful method to learn a disentangled representation. And I'm noticing I did not actually say what they did differently. So what their beta variational autoencoder is actually doing is that they just put a positive factor beta in front of this KL divergence loss term and just tuned the learning pressure. So if beta is high, then they give a lot of weight to this KL divergence term. And well, the disentanglement is more enforced than in the standard variational autoencoder. Good. Now, autoencoding cosmic star formation. What is what we want to do? We will build a variational autoencoder, similarly as before. So in this scheme, you can see we take an input vector x that is encoded to two latent variable distribution vectors, excuse me, mu and sigma, from which then the z will be sampled and decoded to some reconstructed output x prime. However, there's one big difference here, namely this x and this x prime, this describes some set of cosmological parameters. So we could, for example, consider that we investigate 10 cosmological parameters, then this input would be a 10-dimensional vector, and this one would be a 10-dimensional vector, and these store the cosmological parameters, and we see if we can reconstruct them. However, the crucial difference here to the variational autoencoders that I showed so far is that we are not interested in the actual similarity between x and x primed. In fact, we would be rather intrigued to see that the reconstructions are different. What we are instead after is the star formation rate that corresponds to the two. On the left-hand side, this is rather easy to do because it's input data for the whole computational operation. We take we take simulations of cosmological parameters x, and and we get out the star formation rate that is, for example, such a function down here. So this can be achieved by a simulation. On the right-hand side, this is not the case, because if we are training this network and at every training epoch, we are optimizing this output and we are relearning this output. Of course, for every point that we are currently learning, we cannot just perform a full numerical simulation because that would be extremely time consuming. So instead, what we do is we also learn an auxiliary mapping from a set of cosmological parameters x to a star formation rate. And well, this mapping will be done by another deep neural network. And what we have done so far in this architecture is that we have considered that we can approximate a star formation rate as a skewed Gaussian. A skewed Gaussian would be described by 4 parameters. And we simply build a neural network that maps n cosmological parameters, say 10, to these 4 skewed Gaussian parameters. And now what we perfectly have at hand here is an architecture that will learn how to reconstruct star formation rates to get an input of cosmological parameters, output cosmological parameters such that the star formation rates that correspond to the two are similar. Good. Now I'd like to briefly talk about the code. So what I contributed to this project is essentially the code written in Python on this project. There is one script, one Python notebook, where I go through the steps in detail and show what the user would have to type. And the actual program itself is stored in a utilities file. So it should be rather easy to use this script. and I will show some of the functions here. And yes, the whole architecture is written in TensorFlow and Keras. So when we want to perform a learning task, the user will have to set two global parameters that are relevant for the learning question. One being the number of cosmological parameters that is being considered, num params. That's just when you do your numerical simulation, you will know how many cosmological parameters you're inserting, and the same you would of course also set for the learning process. And the second global parameter is the latent dimension. To how many cosmological parameters do you want to compress your input? There's also additional parameters that we will have later, learning parameters, the learning rate, how these neural networks are built, how many layers, how many nodes in each layer. But these are more variable parameters that the user can play with later. So in the first step, we would create some pseudo data, since we don't yet have star formation rates at hand, or we assume we don't have yet. And this would, for example, be inspired by this paper by Lamprisa from 2017, where an analytic function is given that depends on cosmological parameters and is, well, it's just an analytic function of the redshift. We have the low redshift tail, the high redshift tail, and some window function. And this will give us a normalized star formation rate. And one could, just to introduce some interesting feature on our parameters to see if the learning is successful. Also, you take an additional parameter and, for example, introduce an amplitude dependence into that. So these down here would be the two functions to just create input, that is cosmological parameters, and the corresponding output, star formation rates, or I often also wrote SFH, or star formation history. That aside, that was just for not getting confused about one time step or all time steps taken together. It's not so interesting here. What is more interesting now is the actual learning. So as I said, we will have two neural networks that we will build. The one being a deep neural network that learns a skewed Gaussian fit. And here we can work with a simple sequential model like here, where in this example, I chose 7 cosmological parameters, 7, and map them to 4 skewed Gaussian parameters. So we would always map n cosmological parameters to 4 skewed Gaussian parameters. The code here on the left is rather trivial. It's the usual Keras code for building this simple stacking. And we can see here on the right the output. So it's not too interesting. We take 7 input parameters and get 4 out. And these 4 describe the skewed Gaussian. Now, I prepared this small video to show how this would look in the script. So yes, this would be the script, Autoencoding cosmic star formation. And in part 1, we would see how we define the number of parameters as a global variable, and then create data, plot these exemplary out. So this would now be this analytic function that I just described with some amplitude dependence. And now we would build this neural network just with the with the function that with the architecture that I just showed on the previous slide and this output plot. And now here's the actually interesting thing. We compile this model, and I want to make you aware that what is actually the interesting computational part of this model is the loss function, which is not a simple Keras loss function that's implemented, but here it takes some computational effort to describe this comparison of star formation rates that correspond to some sampling, or to, in this case, the skewed Gaussian function that depends on the parameters. So these custom loss functions are then all stored in the Python utilities file. We compile this model and learn it. For a reasonable number of data points, namely 500 and 500 training epochs, we will just in a moment see that the error indeed gets smaller, that we have some nice learning process, and we finish this operation in less than a minute. So that's kind of nice. Yeah, we can now store the respective discrete Gaussian parameters and predicted star formation rates. And here in this function comparison plot, you will see that again in the next, well, in one of the next slides, we will compare the star formation rate that we input with the reconstruction of the neural network that learns discrete Gaussian fit. And we can see that this operation so far is rather successful. There might be some bias with the with choosing an appropriate redshift range and an appropriate scale. So we don't always, well, we are not extremely, I mean, so far, if you do this naively, it will be very good here in this peak because most star formation rates from the analytic model peak around here. And here you will get some weaker fits, but this is all details for later. Yes, so now comes the actually interesting, or the more elaborate part of the learning process, which is the variational autoencoder to map cosmological parameters to cosmological parameters based on their star formation rates. Here, the user would need to create some stacking, some similar to sequential model, again for a neural network, encoder and decoder, and stack them two together into a network that's called VAE, Variational Autoencoder. And I just want to briefly make you aware here that the encoder network is a bit more challenging to code than a simple sequential mapping, because we here have, say, after two hidden dimensions, we learn this vector mu and this vector variance. And then we would insert these into a layer called KL divergence layer. This is the operation that's written on this line. This vector, this layer would just add the KL divergence term to the loss term, so that this is automatically inserted into the added on the discrepancy loss during the training, and one will automatically have this regularizer always inserted into the learning process. This KL divergence layer just returns these two in addition to performing this summation of the loss. And eventually we would then insert this layer, which just returns these two, into an output layer lambda that is doing the sampling. So here we would get the actual latent variables that are sampled. Good. Just to show how this looks, here we would define the latent dimension. And then, because I included so far also parameters alpha and beta to set the strength of our stochastic sampling and of our learning with the KL divergence term, these are so far arguments. One could later remove them and pack this into the utilities file. But so far it might be instructive for the user to see what is going on, what these functions do. So we define these operations of sampling and the KL divergence layer, which adds this term to the loss function. We would build this network, as I just showed. And now we compile this model, where in the loss function, we would have some loss that I called autoencoder star formation history loss that takes as an additional input also actually a new model, a new deep neural network, which is exactly the skewed Gaussian network that we learned earlier. As if you recall the scheme that I told you of what the cosmological parameter autoencoder will do, it will, on the right side of the graph, I explained why we would use a second model in this variational autoencoder. So this is inserted here. Then we train this data. So again, for a reasonable number of data points with a reasonable training epoch, which we will see will yield some successful learning, this operation is performed within less than a minute. So that's good. Now we can store the low dimensional representation, the encoded representation, and then also the decoded representation. And one could compare here for some x values, that is some cosmological parameter tuples. So every line here would correspond to a tuple of 7 cosmological parameters. This would be the respective reconstruction of these. I don't want to talk too much on this, but instead I want to show what's interesting to observe. Or first of all, for this variational autoencoder, again, want to obtain such a training curve that the loss is minimized. One could, I mean, later when we actually do the data analysis, one would of course be a bit more careful about this and would speak more about this. But so far, I only want to explain the architecture of the network. And again, on the we would also obtain some comparison plot here that shows how our input matches to reconstruction here on the normalized scale. And now at this stage, what we have achieved is that we have learned a low dimensional representation of cosmological parameters, namely the latent representation. But we don't know what it is doing yet. I mean, when you train this network, you literally have no idea what these latent variables are. So what is instructive at first is to plot a scatter plot of them to see what's going on. This is done here on the left side, where you can see that the columns themselves are the cosmological parameters, the rows correspond to the latent variables, and you can see that the 4 last cosmological parameters here, this is more or less all just random noise, which I know from the analytic function that is being used to create the pseudo data, this is very reasonable. So our latent variables learn some kind of correlations in here. That's good for now. And on the right side, this plot presents what we used as a regularizer for our training. Namely, recall that this KL divergence term was used to learn a disentangled representation. And disentangled representation means that every latent variable represents a new feature. So ideally, when we scatter latent, or if we find the correlation amongst the latent variables, of course, on this diagonal, we will just have 1 because that's just x plotted against x. But then the interesting information is in this triangle here, where the off-diagonal terms between the latent variables are scattered across all data points. And we can see that here in this example, for example, they are more or less disentangled. Maybe here there is still some entanglement going on. But in principle, these latent variables are expected to represent somehow different features. And this would be then a visualization of what these latent variables actually do to our star formation rates. So this would then finally now, for the end of this talk, be the actual information we want to retrieve. Namely that as we vary a latent variable z, so recall in the example that I showed, we have 5 latent variables. So every plot here corresponds to varying 1 of them. Each of these latent variables is described by a mean and a standard deviation, or a distribution with mean and standard deviation. And now if we just vary this latent variable around this mean in, say, a range of minus and plus 2 sigma, represented by blue and red respectively, we can see that interesting stuff happens to our star formation rates. In particular, we see, for example, that the features of what we would expect as amplitude and peak position, for example, are nicely learned. But in addition, an interesting feature here, for example, is that with the analytic model that I inserted in first place, it seems that the width of a peak is also correlated to its position on the redshift scale. So if a peak happens at lower redshift, it will be with a narrower peak than here on a higher redshift. Well, these variations of star formation rates as we vary the latent variables can then of course be tracked down to the cosmological parameters by varying the cosmological parameters, and one can play all sorts of interesting data analysis games by seeing more precisely what is the peak amplitude as we vary this, what is the width, the peak position, which in skewed Gaussian language would be called the location. anyways. One could then also, if we see some cosmological parameter dependence for varying this, one could ask whether one can approximate these latent variables Z as a low-dimensional, a low-degree polynomial in the cosmological parameters. There's also a function for this available in the script. For the example that I showed earlier for this particular learning of star formation rates by a variation of latent variables, the first three cosmological parameters would be relevant. And we can see that these two latent variables, they leave many of the cosmological parameters unaffected, and they vary around, many of the latent variables, yes, leave the cosmological parameters unaffected, whereas in the first and the last one, we can see a very clear variation. And these two variations correspond to disentangled features according to our learning regularization. So this is a very nice data tool. And now, of course, we can ask what's the outlook of this for future research. And the very immediate outlook is the application of this method to simulated multiversal star formation rates. So far, I've worked with pseudo data, but now this method can, of course, be used also to actually evaluate simulations. Here, one thing that one could worry about is the simplification or also the generalization of the skewed Gaussian fitting procedure of this first neural network. That is, are there many interesting features that are not well captured by a skewed Gaussian? Then one would need to change the architecture a bit, but this should not be too difficult to do. But of course, what is most relevant, most immediately urgently to do is a loss refinement, in that one considers more proper statistics of the loss function in question. And then one can hopefully also find a nice mathematical formalization of the equivalence of parameters by the latent variable representation. Since this variational autoencoder with its mapping to a low-dimensional representation, I hope I've kind of managed to explain why this allows to find the relevant features within the data, and to also see some equivalence between universes with different cosmological parameters, if the star formation rates coincide. So with these latent variables, it would now be nice to actually formalize this in a mathematical language. And then, of course, finally, in the spirit of this DeepThought project, making use of that in a likelihood of life calculation. But this, I guess, is a bit of a longer way to go. But anyways, I thank you very much for your attention. Here is some useful resources for this theme. The first three papers are the computational papers on the respective architecture. The last three are more related to the multiverse and parameters. And especially also for the variational autoencoder and part, there's many resources available online, many blogs that nicely describe that. Well, anyways, thank you very much for your attention.
Just got one maybe sort of technical question. I wasn't quite sure, maybe I missed it, but I wasn't quite sure where you get the link between the output cosmological parameters and the skewed Gaussian fit to train the deep neural network to give you that mapping from the cosmological parameters to the kind of skewed Gaussian star formation rate. You need to have a lot of sort of labeled examples of how the cosmological parameters map onto different skewed Gaussian fits for the star formation rate.
Yes, so essentially we are, if we simulate star formation rates, let me actually show this slide here, since this might be quite useful to see. Here we have some kind of star formation given already that somehow looks skewed Gaussian, and in fact, when you use this analytic function that I showed earlier, that was given in the 2017 paper by Nobrisa, and then also in the numerical simulations that are already available, we have found the general trend that, I mean, this might be proven wrong later, but so far it looks that star formation rates can be nicely approximated as a skewed Gaussian. And so what we would do is we would actually just take these simulated data and insert them into a first network that learns a mapping to skewed Gaussian parameters. And then you would just minimize the chi-squared between the two. So you would literally have one simulation and the standard function description and minimize the chi-squared. And well, these data or other data, because you have now this tool of mapping cosmological parameters to 4 parameters describing a skewed Gaussian. Any parameters and corresponding star formation rates, wherever you get them from, but of course, ideally from a numerical simulation, they can now be inserted into the actual variational autoencoding network.
Okay, yeah. I think that makes sense. Yeah. Yeah. Thank you.
So I was wondering a bit, so you said these are sort of polynomial functions that predict cosmological parameters from the latent variables.
Yes, so these this plot on the right side, now of course this would be written a bit more in detail in the respective function descriptions in the script and the Python file. As we vary one latent variable and keep the other latent variables fixed, we will see that the cosmological parameters are changing. Of course, this is what we want to do. And what we would ideally want is that some latent variables, if we have, say, 5 latent variables to describe these data, and we already know that the skewed Gaussian can be described only by 4 parameters. So it would be very reasonable to assume that one latent dimension, if being disentangled, is completely switched off. Now, if we have, for example, one latent variable that is more or less switched off, that is, say, here, the second column. If we vary this latent variable while keeping all the other latent variables fixed, so we just, we have a mean and a standard deviation for each latent variable. So we just take a latent variable in this range, and we take the mean of all the other latent variables respectively. So we have a tuple of 5 latent variables now, the second being somewhere taken from this range, the others from the mean. And we insert this into the decoder. And this decoder then predicts us cosmological parameters. Oh, yes, it just decodes them to cosmological parameters. And we can see here for a latent variable that is switched off, that the cosmological parameters that are predicted, they do not change as we vary the latent variable, or they change only very little. That's good. That's very nice, because that means our latent variable is in fact switched off, which is this feature that comes with the regularization of the disentanglement. But then there's also latent variables that correspond to non-trivial information, such that these plots here belong together. They are from the same learning process. So if we vary this 0th latent variable, keeping all the other latent variables fixed, we will see, or we see here, that we shift this peak position. We also have a slightly higher peak and a wider peak. And this latent variable corresponds to a variation of the cosmological parameters like this. Blue represents the -2 sigma, the mean of the 0th latent variable -2 sigma, and the mean of, the other latent variables given by the mean of their functions. And this would just be, the variation respectively. Yeah.
Okay, but the polynomial is, in that sense, it's right around the mean is of each respective of like fixed parameters. So it's not like a polynomial that would give you the cosmological parameters for any variation of latent variables.
Yeah, it's probably right to assume that this is happening around the mean, since these would be the respective values that would be learned. So if we have a function, a latent variable z0 here that would have a mean described by a mean given by this number and a standard deviation by this number, then within a reasonable range around this mean, one could check how the cosmological parameters are actually affecting this. So we would see probably, if we did a linear fit here, we would see some kind of positive linear fit in this parameter and in this parameter, and some less positive fit in this parameter. Maybe not, I don't know how the chi-squared would evaluate here, but this was kind of my idea as a step towards formalizing this these mathematics. Yeah, bye, Joe.
You get this information from the decoder, right?
Yeah, so the decoder, yes, the decoder is learned, is a learned model that's not being varied anymore. This is a completely determined mapping where you can just insert now a tuple of, say, 5 values, these 5 latent variables, and you get 10 cosmological parameters out. And so it's interesting to see if varying one value of the input at a time from this tuple of 5 numbers, if varying one number corresponds to a variation of several cosmological parameters, so that we have an interesting yeah.
You could do the same though with the encoder, right? Just the inverse, and then I guess they may look different because perhaps there's a degeneracy of in what kind of star formation they can predict.
Exactly. This is somehow what I meant by formalizing this equivalence.
Okay.
I strongly expect. I mean, I have not gotten to this point, but I strongly expect there would be some surprising, interesting features if one compares how these look for encoder and decoder. Since I was also assuming, yes, this operation on the right side is performed with the decoder. One could as well do it with the encoder, but then it might indeed look very different. That would be interesting.
Maybe a related question on this page here. So in principle, you could expect that you should get, so when you do the disentanglement, that you should get 4 variables, right? Position, amplitude, width, and the skewness for the star formation. But somehow you actually don't get 4 relevant latent variables, but only 2.
Well, from a rough data inspection, it seems to me very reasonable, first of all, that here the location of the peak and its width, they are not separate variables. Just because I've seen over my experience with these pseudo data that were in use, I have seen that indeed the learning learns a very steep peak for low redshifts often, and a very wide peak for high redshifts. This might also be attributed to a certain weakness in the learning, to a certain bias of the respective redshift range that is covered, since for many parameters, I mean, if I randomly draw parameters from a certain parameter space, then what happened in the learning with the analytic function from your paper that I used is that, in fact, we had a lot of these rather narrow peaks here and some wider peaks over here. And so it kind of makes sense that these at least are correlated. And maybe, yes, the learning was also not successful enough to actually observe skewness.
Yeah. But I mean, it does seem to me that it really does learn some underlying relationships, right? Because it just really shows that this analytic function that you've used, it is not random, right? It doesn't produce random skewed Gaussians. And so you sample it and you really do get some constrained distributions from that.
Yes. And
then you really learn it, relationships between you reduce it to essentially 2 effective variables here that describe all these sort of star formations you can get from this function. It's really interesting.
I think I would like to go to ask a few more questions about the plot on the right, because I think I might be missing some fundamental point. So I understand that it shows you how much the cosmological parameters would change upon changing the latent variables while the others are fixed. But so basically the y-axis are the cosmological parameters. And then I was thinking that the x-axis were the latent variables, but then after you compared it with the plots on the left, I understand that the colors refer to the latent variable, which on the left corresponds to the SF.
Yeah, I see. So this.
So is it correct, or am I missing something?
No, in fact, I completely see your point here. And well, I mean, in fact, if you want, the information here looks a bit three-dimensional with y, x, and the color, but in fact, it is two-dimensional. This the x values are completely irrelevant. In fact, this color is actually the only interesting thing. It refers to -2 sigma and +2 sigma. I could have plotted that as just a, what's it called, as a box plot of varying color, where you see if the latent variable would be switched off, this box plot would just be a horizontal line. And if we have some interesting learning, then this might be a box plot that has well, a lower blue bottom part here and an extended red upper part here. So yeah, this axis is in fact not interesting. It's just for visualization. I found it a bit more easy to look at in the end. But maybe I was guided wrong there. Maybe it actually causes more confusion than this.
No, okay, thanks. Yeah, I indeed was thinking that it was some sort of a three-dimensional plot, but yeah, thanks for the clarification. Thanks.